Okay, so we have a project about a smart and secure gateway for the secure Internet of Things. It's a Vinnova-funded project. I'm just going to introduce here and then hand over to Dag. That's he's actually from Imsys. But we're focusing on doing a little bit of edge computing, adding an AI accelerator to IoT gateway. So the IoT gateway is kind of in between the connected internet and the IoT devices here. And we're using Imsys technology. They're one of the partners. They're doing a chip for both the regular application software, like a microprocessor for that, and also an AI accelerator. So we can use that for different types of IoT applications in the gateway. So we have Imsys that provide the chip and design the chip, and we have Uppsala University. They are doing research on like securing and an AI accelerator. Then we have RISE. We have also a use case and project leadership in the project. Our use case is RF fingerprinting, and we have two other companies, SMEs. We have IoT Bridge, and it's kind of says itself. It's bridge monitoring using this IoT gateway and the AI accelerator. And we have Vitra that also do IoT. They are providing locks and asset tracking on construction sites and other applications. So they use it for that type of application. And the main thing we have in the project, it's seen in the illustration to the right. It's the chip, and then it's using the AI accelerator. We protect the AI models themselves, but Imsys will present, and Dag will present more on that in the coming slides. So that's the main thing, the chip itself, and then, as I mentioned, the use cases. And I will now hand over to you, Dag.
Okay, thank you very much. Yes, so let's dive into this execution platform that is on the edge. So let's skip forward to... So first, to say a bit about our take on AI acceleration and why you should do it on the edge. So we want to be close to where the data is, because it can be a lot of data actually that you want to make inference on and or condense in some way to take let the downstream or upper intelligence take decisions, or you have things that you will take decisions about locally, and there you have applications that might be mission critical, so you don't want to send off data because of system failures and so. I use the example, would you like to have a pacemaker as a cloud service, for instance? I mean, so mission criticality, it's resource restricted, but not that restricted with the new technology. You need fast response time at the edge, and there is a lot of data. And you want to do this energy efficient at the edge. So reach numbers like 4 teraops per joule in energy efficiency. So do a lot of operations and potential analysis then. So a short dive into the accelerator architecture. So the workhorses of such an architecture is what is called the processing element clusters here, and that's a cluster of processors. And you can see that the total array, if you configure it full for something that you can run at the edge, it's thousands of Mac units in these processors. So that's the processing elements clusters, and then you have the sequencing in a control processor seen at the top. and you have a network on chip to distribute data quickly. And the interesting thing here also as an edge device that it's very flexible. It can run different types of workloads and it's programmable. And so you see here in the middle then that there is an instruction set for the range of applications that you want to run. But it's definable and you can download the instruction set that you need. I will come into what kind of instruction it is later. But then I said low energy. And so there are several factors here. It's quite a busy picture, but you see that doing an operation in ALU is fairly inexpensive, picojoule, basically, to do an operation. But then accessing memory is almost a magnitude more. The local memories, though, are not that bad, but if you go up the ladder here, you see that you spend a lot of energy. So you want to process near memory, and one other thing is then to use efficient data types. And we are opting for 8-bit integers, and that immediately gives you 4 times advantage over the usual floating point 32-bit data types. But we see that you can use 8-bit. And that's also an important result of the project, that we have shown that these applications can show can produce a good result on 8-bit quantization. And there is a big library then of these functions or for the different processing elements to run different types of convolution operations. And then we come to the actual secure gateway here. And apart from that the application itself is a security application, then also the platform has to be secure. So and tamper-free, because you deploy it somewhere in the network. It's accessible. So you have to protect the memory here, which will be one of the weak links. The accelerator is 1 unit. And so that's what we are doing together with Uppsala University. So we will be able to run the application that is on the right side here. It's the security application from RISE, actually, and be able to run it on the platform in a secure way. And we will not run it on a chip, but we will run it on an FPGA that is part of the project. It's quite a powerful FPGA, so we will be able to represent quite interesting applications on top of the FPGA. And that concludes my presentation. Thank you.
Thank you very much.